Okay, class, so let's discuss some of the topics from Chapter 2. We're going to get through about half of the chapter. So this is for Thermodynamics, ENGR3110. So the first thing we want to consider is some of the things we want to understand throughout this chapter. So internal energy, kinetic energy, and potential energy are important topics in this chapter. We should understand work and the difference between work and power. Heat transfer modes and heat transfer rates, and then power cycle and heat pump cycle are some things that we will briefly introduce at the end of the chapter. Application of knowledge, we want to be able to do calculations relating to closed system energy balances, modeling a thermodynamic case, conducting a thermodynamic cycle system analyses, and then evaluation of thermal efficiencies and coefficients of performance. So we'll talk about what these mean and how to do some calculations specifically for coefficient of performance and the energy balance equation. So the first thing we want to introduce here is work. Right? So work is in units of joules, and remember a joule is equal to a force times a distance. And force is a Newton, distance is meters, right? So Newton meter in SI units. And so it's the mechanical energy performed on or done by the system. You can see below there's the integral of the mass times velocity. If we integrate that with respect to the velocity from some initial velocity to a final velocity, we could also look at it, like I just mentioned, like a force times distance. So if we were to integrate some force that's acting on an object over some distance, let's say some initial location S1 to some final location S2. So this is sort of a general kinetic energy perspective of work using velocity or distance of an object with a certain mass. So if we were to go through our equations, let's say we set these two equations equal and we started doing some integration and derivation. We don't have to go through all the details of that, but we end up getting that a change in kinetic energy for an object is dependent upon its mass and velocity. So you can see that the change in kinetic energy, here we go, so the change in kinetic energy is equal to 1/2 times its mass times its velocity, and the V2 just means final velocity squared, minus 1/2 mass times its initial velocity squared. And so we can say that the change in kinetic energy is just equal to 1/2 times the mass times the change in velocity squared, right? And so this is the work of the resultant force on the body. It's equal to the change in kinetic energy. So if we apply some force to the body, then we can, maybe increase. If we apply a force to a body, we might increase its velocity from an initial velocity. Could be initial velocity of 0, so the body's at rest. If we apply a force, then the velocity, the object would be moving and would have a final velocity obviously greater than 0. A common force that's always applied is gravitational force, right? We've dealt with that in statics. If you've taken dynamics, you should have dealt with that as well. So the work done by resultant force on the body transfers energy to the body in the form of kinetic energy. So this slide isn't so much thermodynamic related. It's just to show that there's other forms of work. And in fact, I won't ask you to do any calculations beyond this slide, but just we'll briefly go over a few different forms of mechanical work, a few different forms of work that we should briefly discuss. So shaft work is a form of mechanical work. It involves rotational kinetic energy, right? So we can have a rotational work that's equal to 2 pi times the rotational speed times the torque applied to the shaft. We have the spring work. So spring work is also mechanical. In this case, we have a linear force, and the PE just means potential energy, right? So the work is equal to 1/2 times the spring constant, which is that K term there. And then we have x2 is just a final location squared minus an initial location x1 squared. We could also have electrical work. So work is equal to the current times the voltage times some over some period of time. So that would be the work that's being done over some period of time. For what it's worth, if you remember from circuits, if you've had circuits, power is equal to current times voltage. And we'll talk a little bit more about how work and power interrelate, but work is just equal to power over some time period, right? If you remember from the previous chapter, we talked about how power is equal to work work as a function of time, or a work per unit time is what I should say, not as a function. So work per unit time. So if you remember, if we were to take a joule and divide it by a second, so that would be energy or unit of work per unit time, that would be joule per second, and that gives us a watt. So in terms of electrical energy, power is equal to current times voltage, and that would give us watts. And if we were to multiply that by a unit of time, then the time would cancel and we would be left back with joules. So that would give us our electrical work. Like I mentioned before, all of these are just examples of work and really aren't related to thermodynamics, but I just wanted to make you aware of them. So here's work from a potential energy perspective. So here we have 1/2 mass times V2 squared minus V1 squared, and that's just our change in kinetic energy. We could set that equal to R could be some force acting on a body, right? So we could have some force acting on a body over some distance. So you can imagine if you had a ball in your hand and you were to apply a force to that ball and move it upward and then release it, you would now be moving it a certain distance. If you look at the drawing in the bottom right, you might move it from some distance Z1 above the ground. You use your hand to apply a force R over some distance up till Z2. Maybe you release it at that point, but essentially you are increasing the height and applying a potential energy. And you know, if you were to look at it from a momentum perspective, you would also be increasing the velocity, most likely, by rapidly increasing its height. And then if you released it, obviously it would have momentum enough to go higher than your hand when you release it. But anyway, the point here is that R is a force on the body over a certain distance, and then we'll have, in this case, we talked about the last slide that we talked about how, or 2 slides ago, how gravity is a constant force acting, or a constant acceleration, which applies a force to a body. And so we would always have gravity acting downward. So in the bottom right, you can see how mass times gravity over some distance would be a form of energy being applied to that body as well. Okay, so let's just go ahead and skip down. We don't have to really go through this derivation. The important part here is that the delta P, the change in potential energy from in this case it's a final state to an initial state, is just equal to mg times z2 minus z1, right? And z is nothing more than the final height minus the initial height. So potential energy is based upon the height of a certain mass or an object.
You may be surprised how much math and physics go into amusement park rides, and more specifically, roller coasters. Common roller coasters don't have an engine, so something has to keep it moving through its fun and intense track. The key to making a roller coaster move is energy. Well, the roller coaster uses a motor to get to the top of the hill. And in the process, it is storing energy for later use, which is called potential energy. Then, you finally get to the top of the hill and gravity pulls you down the track, which increases your acceleration and velocity. This turns the potential energy to kinetic energy. Kinetic is energy that is being used, or energy that is caused by motion. The roller coaster goes faster with more kinetic energy being used, which is why the car gets faster towards the bottom of the hill. The change between kinetic energy and potential energy changes throughout the ride. Eventually, the energy turns to friction from wind, the rolling of the wheels, and the brakes on the track. So you can blame friction for stopping the speed and enjoyment of your next roller coaster ride.
Yeah, sorry about the glitchiness of that video. I think it's because I have a screen recorder and a video running at the same time. But yeah, the point there was sort of showing how, you know, roller coasters are a prime example of how we convert from potential to kinetic energy. And so you can imagine as the roller coaster is pulled up to the top of a hill, or, you know, yeah, the very top of the track, and is released at the very top, it has the highest potential energy. And as it's released, as the roller coaster moves down the track, that potential energy is converting to kinetic energy by increasing the velocity of the roller coaster cart, right? And so that goes back and forth depending on the height of the roller coaster and the speed of the roller coaster.
We're just going to go, we're not going to rehearse. Well, okay. Here we go. Right now, this bowling ball has energy. It's not moving, but it's got energy. Please consider the following. You ready? 3, 2, 1. It looked like it was going to smack me right in the head, didn't it? I mean, it's a bowling ball. It knocked me pretty good. But it'll never hit you in the head. Because when we pulled the bowling ball back from the middle, we gave it potential energy. When we let go of it, it had kinetic energy. The kinetic energy will never be bigger than the potential energy. It's only going to have as much energy as we gave it when we pull it up here from the center. It works every time. Let's give it a push or something.
Energy can be changed from one form to another.
Electricity is a form of energy. You're using some right now. But do you know where electricity comes from? Do you? Oh, come on! A lot of it comes from the heat released by burning coal. The coal makes heat. The heat makes steam. And the steam is running this small turbine. The turbine is actually an electrical generator. And we can read the electricity on this gauge. This is the same way it works in a real coal plant. Except there's more coal, more steam, bigger generators, and more electricity.
Okay, so let's do a simple example on potential energy here. We're going to look at calculating the change in kinetic energy and potential energy of a system that consists of a 1 kilogram bag of tortilla chips, which is falling from 20 meters to 10 meters. Its velocity increases from 15 meters per second to 20.52 meters per second. Right, so as it's falling, the potential energy is decreasing because the height is getting less, and the velocity is increasing as the bag falls due to the gravitational force. Right. So yeah, let's take a minute. We're gonna stop the video here. So please go ahead and get out a piece of paper and pencil. Take a shot at doing the calculation yourself, and we will come back in the next video to discuss the solution.